Welcome to the fourth lecture in lighting. This one is on light sources. And let's start with the natural light source, daylight. And one of the things I have tried to emphasize in class is that our bodies are much more attuned to natural light than any other type of source. So you look normal, your body, your clock acts normally, even your physiology, like maintaining proper vitamin D levels, are more influenced by daylight than any other factor. And of course, when you talk about daylight, you have to have windows and an interior. And when you think about your buildings, I think very often we just sort of look at our building as if it was floating in space and not really anywhere. But really, every building has an orientation, and windows that are on the south side of the building can really have some very intense lighting. And this can, of course, affect both glare and the materials. Northern exposure windows are typically what you're going to see in like a studio for a painter or something like that. It's very even light. It is typically a little bluer. It's a cooler color temperature. And of course, if you're showing paintings that were painted in northern exposed light, you'll want to try and mimic that light color or light color temperature. East and west have more variability. So early in the morning on an east-facing wall in the northern hemisphere, you're going to have some serious glare. And I think any of you who've had early morning classes at Endicott know that if you're in a classroom without windows in the art center, you can have some pretty serious glare. Same with the evening. You can, in say 210 in the VPAC, you'll get some pretty serious glare. And the big reason is the sun moves in the sky. And one thing also to consider is sunlight versus daylight. A lot of people are, we can't use daylight in New England. It's not bright enough. Really, most places in the country have just as much of what you might call daylight as opposed to direct sunlight. And in fact, daylighting is better for interior purposes. If you think of how bright the sky is, when there are clouds, it sort of spreads the sun light around. So the brightest part of the sky, the zenith in the sky, which is the highest point, is only 3 times brighter than kind of the horizon on an overcast day. On a sunny day, that can be 10 times as bright. So, of course, brightness, you can even get glare coming out of skylights under those conditions. So we actually like cloudy days for daylighting purposes. The other thing to consider is that during the course of the year, the extent of the sun changes in terms of its track through the sky. In the middle of the winter, the sun has a fairly low angle. Okay, the angle is called the altitude. The other thing is that its azimuth is somewhat limited. Azimuth is its kind of travel along the horizon. And those of you who have to commute, you might notice that in the spring and the fall, the commute along the highway, depending on which direction you're going, can be pretty miserable because of glare. The sun angle at that time of year is different than at other times of year. So anyway, and how does that affect the interiors? What do we care about all the outside of the building? We care about interiors. And, depending on the configuration of your building, buildings can be designed to reject sunlight in the summertime and yet allow it in the winter by taking advantage of this change in altitude of the lights, the sun, at different times of year. The other thing is that when you are designing interiors, you have control over where the program goes and where what happens at the window in terms of treatment. So, for example, and we'll do an in-class exercise on this, when you're programming a building, do you want, say, a breakfast nook to have direct sunlight in the morning? And if it's an east or west facing window, would it better to be east or west? Because if it's facing east, you're going to get glare in the morning. That may actually be uncomfortable for a breakfast nook. Now, that said, that might be great for a dinner nook. So some thought would have to be given as to where you would distribute that piece of the program. The other thing to consider, again, as an interior designer, you control the lighting. Hey, this is a lighting class. And there's a number of things that you can do, including switching where there are extra circuits by the windows, which shut off either manually or automatically if there's a daylight sensor that says, hey, there's plenty of light here. So let's look at one or two examples. Here's just a kind of, atrium space with daylighting and electric lighting all at once. And what you can see is that it's a very high space. There's a lot of light flooding into the space. Any corner of this space is adequately lit for whatever sort of activity might be going on there, which is mostly, it seems like, sitting around, munching or working on the computer. So the dimming that I mentioned is typically called offset dimming, or daylight switching, you can call it that too, where you might have banks of lights on, say, 3 separate switches. One switch might turn them all on, and then one switch might turn off one circuit or another circuit. Okay. And again, those switches can be automatic or using daylight sensors. Also, when you think of planning out a building, if you're getting into larger scale projects, things like atrium or atria are going to also be subject to the same sun angle issues. So any space facing on those atria, you'll have to really carefully study where is the sun going and how deep is it going to be penetrating into the building. Also, the angle of the ceilings within those interior spaces can act as a reflector. See here, the light comes in from a low angle in the winter, hits this angled ceiling, and that, because of the angle of incidence on that ceiling equals the angle of reflectance, you get light pretty deep into the space. Now, of course, the diagram dramatizes it, but you can calculate that, and this dashed blue line represents actual calculated values of what you could expect at different that particular time of year as for light levels. Obviously, it is still quite bright by the window, but can't avoid that because windows are just bright. So anyway, there's a number of other strategies which you can use as an interior designer, which we'll look at here. These include light shelves. Obviously, skylighting is something that you can suggest as an interior designer. Of course, you'll want to make sure that you get somebody to look at the structure of the building before you start dropping in skylights willy-nilly. But it is great for deep buildings. The example that I like that's convenient is Costco. They save a tremendous amount of money by skylighting, and they all use it as a rule. There's a couple of other things: light pipes, light wells, and then things like integrating the HVAC systems so that they run along windows and can act as, say, a reflector or to help in controlling the light. Anyway, typically also when you're controlling windows, light at the windows, vertical blinds are typically more effective on the east and west windows because they're better at cutting off those variable low-angle glare. Horizontal blinds on the south and the north are fine. Of course, you can use any type of blind on any window, but that's a sort of rule, or not a rule, a suggestion. Anyway, and then let's take a look at the actual examples here. A light shelf works by reflecting daylight into a space, bouncing it off the ceiling. And here's an actual example. And this one even has that sloped ceiling that we saw earlier. And what the advantage of light shelves is that the person by the window, if it's bright, they're going to drop a shade in front of their window. The light shelf kind of prevents them from stealing or blocking light from other parts of the project. And here's another example of sort of a light shelf. In this case, they've actually used the HVAC duct. They've specified a very wide duct, but the advantage is it's reflective and helps create light, bounce light into the space. So light pipes, they're just a product basically that you can buy. They fit in between the joists and the rafters. They're spaced to fit. And they're actually quite effective. I've used these in my own work, and they do a surprisingly nice job. What's terrific is when you put on an addition, say, and you've blocked a window to a toilet room, This can provide natural lighting in the toilet room. Of course, that makes you look healthier and is terrific when you're putting on makeup and other stuff. And I've even, this is an example of a sort of tunnel of light that they've created using a skylight and then reflecting it off of kind of a giant, I don't know, mirror, really. And it ends up backlighting this very nice glass wall. And the advantage of this is a giant convention center in Dallas or Austin or something like that, is that you get some variability. Even when a cloud passes overhead, the wall kind of changes, and it's a free, easy to install effect. You could even integrate electric lighting with this for nighttime. And then, again, like I mentioned, skylights. I think we've seen these, and you can have fun with these, of course. And as I mentioned, integrating them with electric lighting so that you get a similar effect day and night. One of the things about controlling daylighting, there are many methods. I've noticed that as you guys do your projects, almost nobody does anything on their windows, which is kind of sad because it's a big nightmare, frankly, or just a design opportunity. Of course, the glazing systems can help you in terms of the low E and all that. They can prevent heat or prevent heat loss. Glass coatings can do a number of things, including also prevent heat gain or loss. But the thing that has the biggest impact on design is window treatments. Obviously blinds, draperies, shades, all those sorts of things. And what you don't want is the client to sort of add on some junky stuff after the fact. You really want to think these things through. If you're working with an architect, you can also discuss roof overhangs and awnings. And window films, there's actually a link here to 3M is a big company that makes, they're basically stick-on films. They can be pre-applied or applied after the fact. And they can come in colors, they can be polarizing. And this is the kind of thing, if you have windows facing an ocean, for example, you might want to polarize them. If you're in an area subject to hurricanes, you can get ballistic film that is integral with the frame of the window, and it will actually prevent your windows from smashing in a hurricane. So, anyway, and then there's all sorts of shading devices, but the non-residential ones are ones that we should actually be familiar with. Lutron Sivoia is one that is in the good old VPAC 206. And these are very nice systems. They're typically rolling up into recessed slots, or they can roll sideways. There's a million design options, and the percentage of light that passes through the material can vary. And then there's all sorts of ready-made settings, but they can also be configured to work with daylight sensors. So if the daylight sensor or programmer determines that it's going to be too bright, they can drop the shades as needed. Even the switches can be changed, and this is something we'll talk about later on. That why spend $50,000 on a shading device and then buy a crappy plastic switch plate cover? Spend the extra dollar and get the nicer cover. So anyway, it's all about controlling glare. And of course, the aesthetics of the project and the view in and the view out are worth considering as you look at these things. Even things like veiling reflections, are going to be things you'll want to consider. Sometimes you see some very nice instances of the shape of the room being designed around a daylighting effect. This is the Kimball Art Museum, the original one in Fort Worth, Texas, by Louis Kahn. And what happens is a slot was designed in this barrel vault, and light comes through the slot and bounces off these scoops. So you get this kind of indirect lighting effect. In fact, it's almost like a double bounce. It bounces off of the scoop onto the arch, and then from the arch, or the vault, down onto the artwork. It's very nice. They also did a good job in this design of integrating the HVAC into kind of the overall planning. Again, when you think about lighting, you do typically think about HVAC because they're all often happening up in the ceiling. Anyway, other things to fiddle around with, something like changing the shape of the aperture of the window. We can do this as interior designers. You may be stuck with the square window, but you can certainly have some fun with it on the inside of the building. And, what's so magical about square? If you're working with an architect designing a new building, you can choose whatever sort of window you want. And there's an architect named Tadao Ando who is a fine architect from Japan who does a lot of work with daylighting. And he often designs his spaces. They're super minimal. He designs them to have very interesting reflections and kind of gradients of daylighting. And the daylighting in his projects comes through these strange-shaped apertures and in all sorts of different and unexpected kind of locations. And there's usually some goal, either creating a shadow that's going to move over the course of the day or controlling a view through one place or another. Whenever you're using daylighting, if you actually want to figure out if you're going to have usable daylighting, there's something called the daylight factor, and this is something you can calculate. And there's wildly complicated ways to calculate it, but you guys don't have to worry about that. All you have to worry about is the magic 2.5H. In fact, I'm sure that's going to be on the test. And because it's like the simplest formula you're ever going to see, H equals the head height of the window. You have a 20-foot high window, 2.5H is 50 feet. That means that within 50 feet of that window, you'll probably have pretty decent ambient light levels from daylighting. As I mentioned, there's many other factors, especially the orientation of the building. But what this tends to lead to is the alphabet buildings. And the reason that when you see old buildings that were designed for use with daylighting, they tend to look like a letter of the alphabet because of the limitations of the 2.5H. Most of these buildings, if you sat down with a piece of paper, you could figure out they're all 2.5H, and they're all shaped like E's and L's and that sort of thing. Anyway, other people have used different ways of getting daylight deep into the building. This is Alvar Aalto, and he has these daylight kind of cones, but he also has these very unusual scoops that are designed to work with the shape of the plan and kind of create interesting lighting that reflects throughout the space as the sun moves during the course of the day. The sun is going this way, and the reflections kind of spread it evenly in this fan-shaped space. And this is a section through those buildings, and you can see there's a kind of a parabolic effect. In fact, this is a double parabola. Also would do a lot of daylighting studies and kind of figuring out where the daylight would reflect. So anyway, just to take a look at one church as an example of a church designed around daylighting. This is Tadao Ando's Church of Light, and obviously those of you who are Christian might know that there's some symbology to the cross shape, and that's played on by making it a window. Obviously no stained glass in this particular tradition, but you can see it's just a very nice kind of symbolic focus-grabbing use of daylight. And yet there's still enough daylight in the space to orient. Basically, this space could probably operate without any electric lighting if needed. And just highlights the geometry and the simplicity of this space. So, anyway, there's a number of terms that have to do with daylighting, which I won't go into every single one, but things to be aware of. And also be aware that when you are using daylighting, you can save money for your client by switching to daylighting, and these values can be calculated based on the electric rates in your region. So let's chat about chapters 9, 10, and 11, which are historical light sources. Basically, we're looking at filament light sources, low-intensity discharge, and high-intensity discharge. And these, I'm actually gonna tone down the depth of the lecture here, just because we really don't need to talk about all of these lamps that much, other than to recognize them as historical. But the things that we want to learn about these is, what kind of light output do they have? What is their efficacy, which is how much light do you get out of that source, and the color, the lamp life, other elements related to the lamp. The big thing is that as history has gone by from filament sources onto low-intensity discharge and high-intensity discharge lamps, it's all about increasing lamp life and increasing efficacy. Okay, And also, as we've adapted these new sources, the heat load on the building has become a bigger and bigger impact. Back when we just had a small amount of incandescent lights in a building, they produce a lot of heat, but we tend not to use a lot of them. They are inefficient, so very little of the light comes out as very little of the energy is converted to light. Whereas as we jump to fluorescent fixtures, more of the energy is converted to the light, but there's a lot more heat too. In fact, what you'll see, even in good old New England, an office building in Boston, the heat from all the light sources collects in those buildings, and they're running their air conditioning into November, sometimes December, because of all the heat in buildings. And even with our new LEDs, they generate a fair amount of heat, so not as much as incandescent or fluorescent, but definitely a consideration. So one of the big things to learn about historic lamps is you typically name particularly filament lamps by the wattage, the bulb shape, and the bulb size. So the wattage, the typical wattages might be 25, 50, 100 watts. Bulb shapes we'll look at in a second, but the most common one is A. A stands for arbitrary, which seems kind of random to me, but that's what they use. Anyway, and then the bulb size, interesting enough, it's measured in the US in eighths of an inch. Why eighths of an inch? I don't know. Ask Thomas Edison. But basically, so what you end up with a common lamp is a 100 A 19 eighths of an inch. That regular old lamp that you can go and buy at the hardware store that we see everywhere, that is an A19 lamp, and 100 is the wattage. Okay, so let's look at a couple different features of the incandescent lamps. I don't know why I still have this animation in here. That's kind of silly. But basically, they're burning something. That's how the historic lamps work. I think I talked about that a bit in the historic lecture. Big thing to recognize, this is the bulb. And the bulb is typically filled with a vacuum that has a filament. That's how they all work. And you can get them in a million different shapes. It's amazing. This is just touching the surface here. It's amazing how many incandescent lamps there are out there. In fact, a little bit of trivia here, a three-way lamp has two filaments in it, one for the lower wattage, one for the higher wattage, and then one where they're both on. So there's a little trivia. Anyway, like I mentioned, they're not terribly efficient. A lot of their effort goes into generating heat. So nice thing about incandescent lights, they're super flexible. Reflector incandescents, and these are things like PAR lamps, PAR, Parabolic Aluminized Reflector. These are typically used when you need a high degree of light control. Okay, so when you specify particularly PAR lamps or ER or MR lamps, those are ones you're going to want to aim at something. When we were wandering through the mall, we saw a lot of PAR and MR lamps. Okay, and here's just a simple diagram from the book about the light distribution and how the beam spread changes. So, and these beam spreads typically are using, when they describe them in the catalog or in the manufacturer's information about a light fixture, what they accept, they use these codes. These stand for spot, narrow spot, very narrow spot, wide flood, medium wide flood, very wide flood. And these are angles. Okay. Some manufacturers, I believe Philips has started just putting in the angle in there, 5 degrees, 10 degrees, 20 degrees. And these reflector lamps, they're so common that you'll see them in your backyards, but you're starting to see replacement lamps that are LED. So Tungsten-Halogen Lamps are really just the kind of lamp that, again, is going to be a historic lamp. They do have a higher efficacy than regular incandescent lamps, which is to say they produce more light per watt. And this is thanks to the halogen effect, which is in the, typically this is a vacuum inside the bulb. they've replaced it with halogen, and that has a funny way it reacts with tungsten, and it kind of replenishes the filament before it can burn out. So these tungsten lamps, they tend to be super bright, so you'll see them in instances like an MR or these PAR lamps where you need a high degree of optical control and a small lamp size. This is a very skinny lamp, and this is something you might see in a car. Again, there's a million different shapes. Fluorescent lamps, there are also a lot of different options with fluorescent lamps. And basically the way they work is electrical current passes through some, again, tungsten, just like before. But in this case, it's a tungsten cathode, which is basically it's a bare wire. You have a bare wire on one end of a tube, a bare wire on the other end of the tube. Those are called cathodes. They run enough current through that thing at a high enough voltage that there basically is a lightning bolt crossing between them, and that excites the gas inside the bulb, and voila, you've got light. And here's the cathode. There's phosphorus on the glass. There's also mercury inside there, and often there's what are called rare earths. And fluorescent tubes, they are super efficient, 8 times as efficient as incandescent lamps. And they last a ton longer, thousands of hours instead of hundreds. However, all that junk in there is really bad news. In fact, you should never throw out a fluorescent lamp into the garbage. You should dispose of it properly because of those hazardous chemicals. That stuff is bad news. So, fluorescent tubes come in a number of sizes. Typically, they are labeled T for tube, and then the dimension in eighths of an inch. So T5s, I believe somebody discussed that in one of their precedent studies. That's 5/8 of an inch in diameter, whereas a T12 is 12/8 of an inch. And there's different size lengths of lamp and also bulbs. Typically 4 feet and 8 feet are the sizes we use here in the U.S. So the ballast is also a factor with the fluorescent lights. We're not going to really worry about ballast so much, other than to say that they exist. Compact fluorescents are basically fluorescent tubes that have been shrunk and twisted around to fit into smaller light fixtures, and they're meant to replace incandescent lights. They're basically garbage. I really don't like them. They take a while to warm up. The only advantage they have is that they were this nice transitional technology while we were trying to save energy, but before there was a higher efficiency option. High-intensity discharge lamps are another high-efficiency option. The way these work, as opposed to the low-intensity discharge, which is fluorescent lamps and neon, these often have a tube inside it, and instead of filled with a hollow and filled with a gas, often the tube itself is what they're arcing electricity across, and they are super bright, have good optical control, but the color rendering is not so terrific. And these are the kinds of things you see in gymnasiums, for example. In fact, at old Endicott College, we have HID lamps in our gym. And these guys, they produce a tremendous amount of light, but they have a giant ballast, very heavy ballast. In fact, you often need a little motor connected to it to bring that thing down so you can change the lamp. So, anyway, they also come in a variety of shapes, and you can get them with high degrees of optical control. So they can be nice for things like lighting a facade, where the color rendering isn't quite so important. One thing to consider with all of these light sources, but particularly with the HID sources, is they have what's called a restrike time, where if you turn it off, you think of like a baseball stadium. If the lights go out by mistake due to a power failure, it can take 10 minutes to start those guys again. Anyway, so those are historic light sources. I know the book has full chapters on them, but I do feel like we actually don't need to know as much about them as we do need to know about LED, light-emitting diodes, or solid-state Whoops, I cut my text off there. But basically, the thing about LEDs that you need to know is that it's goodbye incandescent lighting. LEDs are going to replace pretty much all forms of electric lighting, except possibly some HID lights, because they are so efficient and easy to control. And they typically, as we might have discussed in class, are these little flat chips that glow, and they also often encase it in some kind of lens case or lens-like device that spreads the light. So again, here's the illuminator. It's a flat chip. So one thing to consider is that, here I'll use my little pen, light can only go out from that surface. It can't go down from the surface. So it's omnidirectional. And in fact, you don't even get much light going sideways. It's almost exclusively going perpendicular to that chip. And the way these guys work, it's like super, complicated. But basically, there's a kind of heat sink, and this circuitry is printed kind of in layers onto a chip. As they glue more stuff on it, this thing gets deeper than it is wide. So, and if you're wondering about the physics of it, well, I don't really understand the physics. There's something about P and N metal plates, and something about the electrons jumping from one to the other and emitting light when they do that. That's about as well as I understand it. The basic idea is that this chip is what emits the light. Okay. LEDs are not easy to just plug in. You need to have, they're very sensitive to voltage and current. So you, most of them have what's called a driver, which essentially is a ballast. The driver controls the power that comes out both in voltage and in current. And when you have a lamp that is trying to fit into the existing built environment, so this is a screw-in lamp. It looks suspiciously like it has a filament, that little glass thing, but really what it's doing, it just wants to look like it has a filament. These are the little LED emitters. They're placed onto these chips. Again, they're unidirectional. A filament lamp is omnidirectional. It's just a glowing thing. It spreads light in all directions. So they really have to do some monkey business to get enough LEDs glowing in enough different directions to make light in different directions. And there's a million variations nowadays, now that LEDs have become so cheap. Each one has its downsides. This one, for example, very common. The light in this one only goes out from this, essentially a bulb. These are typically plastic because it doesn't need to contain a vacuum. The problem is, this is great if you screw this light into a socket, say up in a ceiling, because you only need light going in that direction. However, if you have a light fixture by the side of your bed that has a shade, that shade, if the shade is kind of shaped like this, well, there's going to be no light down here. The shade won't look correct. So anyway, each of these, as they do their hijinks to get the light source to look like it's supposed to, has its advantages and disadvantages. And that's something which is just based on the fact that we have all these old pieces of equipment that we're trying to use LEDs in. This also includes directional lamps. Now, directional lamps are more suited to LEDs. They still have the screw-in or plug-in base that you'll see from historic lamps, but each of these little yellow sources is omnidirectional. I'm sorry, I keep messing that up. Unidirectional. So they're only going in that direction, and of course that is perfect when you want a directional light source. Again, the type of base is meant to fit into all sorts of things. And some of these, it's just ridiculous, the hijinks that they go through. Even fluorescents can be replaced. Of course, the typical thing here to worry about is that getting those LEDs facing in the correct direction. Once again, LEDs, unidirectional. Fluorescents, sort of omnidirectional. They're more of a linear source. So anyway, other things you'll see, this is a screw-in lamp that has an adjustability to it. So you could screw it into a recessed can, and now you can actually focus the lights a little bit The one that LEDs excel at, and is a nice design technique, are these ribbon lights. Essentially, they're super flexible. They can have any degree of brightness that you want. You can control the light output and the color temperature, so they're super handy. Anyway, and then you have other things like in office ceiling systems. You can still get troughers with a lens on them, so you don't have to rip down your entire ceiling to replace them. So, in the 21st century, I think that the best way to approach using LEDs is to integrate the LEDs with the fixture. LEDs, because it's a chip, you can squeeze it into really thin places. And so different types of light sources can take advantage of that. You don't need to have these screw-in lamps anymore. And you can actually use that as a kind of design aesthetic, depending on what you're trying to accomplish. So to kind of go over the advantages of LED, you can make them into any kind of bulb shape if you want, incandescent or fluorescent. They have an incredibly long life, 20,000 to even 100,000 hours. This is opposed to, for an incandescent lamp, about 800 hours. For a fluorescent filament lamp, that might be 1,000 hours. For a fluorescent tube, it might be 3, 4, or even 8,000 hours. So it still is quite comparable, and the efficacy is as good as you're going to get in HID lamps, but they're dimmable and have a relatively high color rendering index, typically in the 80s. So they're absolutely a terrific light source. There are variations on LEDs, including OLEDs, cold cathode, and neon, and fiber optic lighting. Those are odd types of lights. Really, cold cathode is low intensity discharge, and fiber optics typically use metal halide. So, when you're working with a client and they say, "Hey, can I save money replacing my bulbs?" Of course you can, and there are ways to figure it out. And this is I like this graphic because it's easy to read. I can just look at the pictures. I don't have to read any of this junk. For the same lamp, so these all emit the same number of lumens in more or less the same pattern. Again, each lamp is going to be slightly different, but you can get a pretty good sense of the lifespan and the overall cost. Now, this was a while ago, so it was $45 per bulb. It's come down quite a lot. But if you look at the wattage that these require, this is only 20 watts, and this is 100. That is very significant when you're looking at an entire building. When you're talking about lamps, there's a number of different terms, just like when you talk about daylighting. One of the things that is probably the most important is efficacy, the amount of energy that is converted into light, and that's measured in lumens per watt. So the upshot of all this, LEDs are basically going to replace most other lamp types, so we better get used to them. And the lamp, per se, is actually most typically integral with the fixture because they last so long. By the time the lamp burns out, it's basically time to finish with the fixture. You have to throw it out. So most of the time, it's just easier. And that is that.